All right, let's get started. It's a special pleasure to introduce Alex Kusenko, who is a professor of physics at UCLA and Kavli Institute in Tokyo. Alex got his undergraduate degree at Moscow State University and PhD at Stony Brook. He went for a couple of short postdocs at University of Pennsylvania at CERN, I believe, and then as a faculty member at UCLA, where he has been. I very clearly remember his talk at Rutgers when I was a graduate student and he was a postdoc. He was talking about cue balls, and back then he resurrected that subject, which was forgotten since the work of Coleman, and put it in the right context of particle physics and what may be realistically produced and observed in the universe. And by now that's a very famous paper. It was very exciting back then, I remember. And since then he's written a number of influential works in astrophysics, cosmology, astroparticle physics, and today he's going to tell us about black holes, called rush for black holes.
Well, thank you very much. Thank you for this very generous introduction. As Greg said, I come from the other side of the Hudson, and I don't come out to the city often enough, so I'm very grateful for the invitation and for the opportunity to be here. So I'll talk about black holes, and that will be unifying themes for two separate stories, both of which I think are fun stories to tell. And of course, since I do come from the West Coast, gold rush is natural theme, but there's also a connection with there's so many papers and so much excitement about black holes due to LIGO discoveries and other interesting developments that it's fun to talk about black holes. So these are some famous black holes. This one is in the center of our own galaxy, and it is seen by the motion of stars. Otherwise, it's pretty quiet. It's one of these starving black holes that don't get fed enough. If you throw enough material in the black hole, however, it becomes a source of all sorts of energetic particles. And of course, nothing comes out from inside the black hole, but while this stuff is falling into the black hole, it can heat up, can produce a lot of radiation, can form jets. And so this is a picture of two jets from a supermassive black hole with billion solar masses, whereas our galactic black hole is only a few million solar mass. And then there are black holes with masses of tens of solar mass. For example, this one at Cygnus X. Some of the signals that we see from these objects come in the form of gamma radiation, and some others come in the form of cosmic rays, gravity waves. So gamma radiation is formed in the jets that these supermassive black holes form, and we observe the highest energy gamma rays with the help of Cherenkov telescopes. There are 3 currently in operation, and soon enough there will be a new fantastic instrument called Cherenkov telescope array. Right now, so this is a HESS, this is MAGIC, and this is Veritas, and they use this technique that looks at the shower of charged particles that arise from a gamma ray interacting in the atmosphere. They collect the shower of particles on the ground, and they reconstruct the energy of the initial particle and the direction it came from. Another technique is to look at the charged particles that go through water tanks, such as this high-altitude water Cherenkov detector in Mexico. And this, again, gives you an alternative way to observe these particles. And finally, there is a remarkable instrument, Fermi Gamma Ray Space Telescope, out in space, which is not big enough to see the very rare highest energy TeV gamma rays, but it's very, very good precise instruments for 100 GeV and lower energies. And if you look at the results that, for example, the spectra of these gamma ray spectra from 2 black holes with these telephone numbers, then very soon you will see something remarkable. They are color-coded by the experiment. And the remarkable thing is that there is nothing to see here. It's just a straight power law with no features. Whereas if you were paying attention in school, you'd know that people expected to see a dramatic feature, namely a cutoff around 1 TeV, due to the absorption of these gamma rays on the photon backgrounds. The universe is filled with photon backgrounds. The most numerous photons in the universe come from the Big Bang. It was a very big bang, so if you unplug your TV from if you unplug your grandmother's TV from antenna, it shows that static, and 5% of that static comes from the Big Bang. But there is also a ubiquitous field of infrared
I think
photons.
that's only if your grandmother's telescope or television is in the backyard.
Right, that's right. Well, I mean, my grandmother, see, I grew up in the Soviet Union. It's like a time machine, right? So at a given time in the Soviet Union, you were a century earlier. So, so my
Your house
grandmother,
is for transparent to microwaves.
that's right. My grandmother has something to learn from your grandmother. All right, anyway, so, but so there's an infrared background that is created by stellar starlight, which is absorbed by dust, reprocessed, re-emitted in infrared, and it's ubiquitous. It's hard to measure locally here because sun produces too much infrared glow, so-called zodiacal light. But people have these inconsistent measurements, but there is a lower bound that you can set on the density of infrared background, and that just comes from counting of galaxies. And you see the starlight and you can say, okay, this is the lower bound. And even with that lower bound, you'd still expect that the gamma rays of the highest energy would interact with these photons, produce a plus and minus pairs, lose energy, and you'd see a feature in the spectrum, which you don't.
And that feature would be a sharp cutoff. Right?
That's right.
Just be a cutoff.
That's right. And so people, of course, let's see what you need to do at the source in order to avoid seeing that cutoff, that absorption. Well, it turns out that if you de-evolve the spectrum, you'd need accelerators with the index of the power law, which is less than 2, which means that your next decade in energy has to carry more energy total than the previous decade in energy. And even if you're building an LHC type accelerator, it's hard to achieve that. Okay, and even harder to expect this to happen from just a natural astrophysical accelerator. Even more you don't have to be an astrophysicist to see that there is a problem here. If you look at the spectra of different blazars color-coded here, so these are the measured spectra, okay? But these all come from different distances, so they have to shine through different thickness of this wall of photons. So what should the spectrum be at the source in order to arrive here with this slope? Well, it turns out that they all have to be different, and they have to conspire. They have to know about the redshift from which they are coming from. And people tried and failed to explain this with selection effects. And more generally, if you discover some phenomenon, you usually discover universality when you understand the phenomenon. But something is wrong if your observed spectra are all universal and your intrinsic spectra are all different. Then you must be missing some important piece of physics. So that's the problem. Well, softening of the spectrum is another way to look at this. If you look at the spectral index at GeV and the spectral index at TeV, one of them should not suffer from absorption because you're below the plus or minus threshold, and the other one should be absorbed, right? And this is not rocket science. We can just work out the relation, how it should scale with the distance, and that relation was worked out, and the nearby blazars are all agreeing with it, but the distant black holes shine with something that, something goes wrong with the distant sources. Something different. Okay, and for every puzzling phenomenon, there is a compelling, exciting particle physics explanation. So, if there are axion-like particles into which a gamma ray can convert in the magnetic field near the source, and which can then propagate through the universe and reconvert into a gamma ray in the magnetic field nearby, then this energy can be transmitted, avoiding the losses in the field of intervening photons. Okay? So that's one possibility that people actively pursue. In fact, one of the science goals of the CTA was listed in the proposal as search for axion-like particles motivated by this anomalous transparency of the universe. Also, if at these very, very high energies, the Lorentz invariance doesn't work the way we think it should, if the Lorentz invariance is broken, then E plus E minus processes may not take place. So that would be another way to explain this puzzling behavior. And of course, these would be very exciting possibilities, but before one can make a claim, one should examine just usual physics and see if that works. And that's what we decided to do with a very bright graduate student, Warren Essig, who came to UCLA and who is now in the audience here. Well, so this picture was taken at the University of California research facility on the island of Moorea in French Polynesia, where you see 3 of my graduate students hard at work. And we organize a conference there every year called Pacific. That stands for Particle Astrophysics and Cosmology, including Fundamental Interactions. You have to capitalize 2 letters in interactions, but no one complains. And so please be our guest and come and visit us. And so that's when we, Warren and I decided to look into possible standard model explanations of this phenomenon. And the first thing we thought about was that the same jets that produce gamma rays are also expected to produce cosmic rays. Now, cosmic rays don't reach us from the same point because they get bent by the magnetic fields, most significantly by the magnetic fields right here near the detector. So what cosmic ray detectors observe is a bunch of cosmic rays arriving from some random directions, not necessarily pointing back to these sources. But there's a strong suspicion that these jets, where the shocks accelerate charged particles to produce gamma rays, also are responsible for the acceleration of protons that we see as cosmic rays. Now, these protons can travel across the universe without significant loss of energy if their energies are below so-called GZK cutoff, which is 10 to the 19 electron volts. But below this, let's say 10 to the 18, there's just not a significant loss of energy. But they do interact with the intervening photons, and these interactions could cause, say here, pion production or E plus E minus production, which reintroduces a new photon, the secondary photons, right? So the interactions of protons along the line of sight with intervening photon backgrounds can produce additional gamma rays. And the scaling of that luminosity, of that flux with distance, is very, very different from the primary gamma rays produced at the source. Because for the primary gamma rays, well, there is 1 over distance squared. Every source in the world shines with 1 over the distance squared. And then there is absorption, which is described by this exponential, where d is the distance and lambda is the mean free path. Now, if, however, instead of just absorbing photons, you use this wall of intervening background photons as a target, then, of course, the thicker the target, the more you produce, but you also lose. And so when you fold it all in, the luminosity scales with distance as 1 over distance or 1 over distance squared, depending on where you are with respect to absorption. But in any case, you don't have this exponential, which is a big deal. So it's not a matter of whether secondary gamma rays are important. It's only a matter of where they become important, right? If you filter out the primary gamma rays with this exponential, then you're looking at the secondary component. And so then we calculated these spectra, meaning Warren calculated these spectra very accurately, taking into account all these effects, including what I will discuss later, deflections in magnetic fields and everything. And so we get a remarkable agreement with all these unusual spectra for the cases where, where the standard just primary photons would fail. So for example here, if you look at this, the primary component was about to go down and miss all these 5 data points at the end. But then there is a secondary component which you can see coming in by the spectral break, and it explains the spectrum of this blazar. So incidentally, that's the phone number of the blazar. I want you to remember it's one of the famous blazars because of its strange behavior. And so for every blazar that we could find, we observed that behavior, and the agreement was very good. The only parameter that we use here, we don't have any control over the shape of the spectrum. The only parameter we use is the overall luminosity in cosmic rays. And we choose it to be within the range that, we choose it what we need to explain, then we compare it with what theoretical models produced, and it's right in the middle of the range where theoretical models expected.
Most of this production is happening very close to the source, presumably.
No. The proton just marches on and keeps producing.
Yeah.
What you are seeing is the gamma rays produced closer to you, because
Okay.
the others get filtered out
And the
just
reason
like
the
primary.
source still appears as a compact source is
Sure.
because it's line of sight.
Because
of
the proton is not deflected significantly,
I see.
which will be important in the
I
next
see.
5 minutes. Exactly. Okay. Right. So also, one remarkable thing is that as you vary the spectrum of protons, we varied the spectral index or maximal achievable energy, nothing changes with respect to the gamma rays that you are observing, because all these processes happen at the thresholds. They don't really care about the shape. The only difference occurs at energies where you never hope to see anything. And the other observation to make here is that neutrinos have a peaked spectrum, right? So on the left shoulder, it's pion production threshold. On the right shoulder, it's protons. There are too few protons. Okay. But the interesting thing is that gamma rays, the shape is so robust, and that means that measured spectra are so robust in their shape, right? So they're all the same in their shapes precisely for that reason. No matter how far the source is at these highest energies, once you filtered out the primary gamma rays, you're looking at something that was produced nearby. And it doesn't matter how far that source is, right? And that explains this universality of spectrum. The energies come out reasonable. This is a nice source. This source is so far away that it would have never been observed by any telescope if the redshift was known. But the redshift was not known, and Veritas spent 50 hours observing that source and obtained the spectrum. And only after that, optical astronomers measured the redshift by an absorption line somewhere along the line of sight. And I don't know whether absorption occurs at the host system or somewhere in between. So that gives you a lower bound. But that's the most obscure TeV source so far. And you see that the primary component would have missed all these data points, and the secondary component comes in and fixes that. Also, if you look at that diagram, now we understand, again, because the gamma rays that you observe are produced nearby, then the spectral shape, the intensity depends on where the source is, but the spectral shape doesn't, right? So it doesn't matter where the source is. What you're seeing is the stuff produced nearby. So that gives one a satisfying feeling. We figured something out. That's interesting. It also gives one an opportunity to look where we didn't expect to see anything, right? So this is how far you can see in photons of a given energy. And this is the slide that Francis Hausen likes to put up for to highlight the advantages of neutrino astronomy, because neutrino astronomy doesn't get opaque here. But we chip out a little bit of a space here from Francis's universe, and it becomes a little bit more transparent, which means that we can see farther and we can see more sources. And this was quantified by these people. They're predicting that CTA, the next generation telescope, will see tens, if not 100, of these very distant TeV blazars. And then we can do a lot of interesting stuff with these new data. Okay? And I don't have time to talk about time variability unless you ask me, because I want to tell you another piece of this puzzle that comes with the ice cube detector observations of neutrinos. Now, this is a remarkable detector. It's at the South Pole. South Pole is a mountain covered with ice. For Glenis and other skiers in the audience, the description is it's a mountain that has 5 centimeters of powder, 2 kilometers of base. And the ice base is where the experimentalists drill holes with hot water, and they insert these arrays of photomultipliers. And when neutrino comes through, it passes by this Eiffel Tower, which I don't know why they put an Eiffel Tower there, but it just swings by the Eiffel Tower and then produces muons and electrons that produce light, and the light is recorded by the photomultiplier. So this experiment reported a remarkable discovery of neutrinos with PeV energy. Now, they were looking for neutrinos of higher energies, which they didn't find. And they were expecting to see neutrinos at the lower energies, which they did find. But no one expected neutrinos at 1 PeV, which they found. And these neutrinos are not coming from anything that you recognize very easily. Right? So normally, if you look at the sky, the brightest sources are not, the sun is the brightest source of photons, not because it's the best star in the world, but because it's the closest one. Right? In the same way, in neutrinos, you should see nearby sources more prominently than the more distant sources. That's not what IceCube is seeing. They're seeing very distant sources.
Is that just the PeV photons, or is that all their photons in some wider band?
That's in a wider band, and PeV are part of this. But so now, when I said nobody expected a PeV neutrinos, I really didn't mean that, right? Because we did, and we actually published this spectrum that I just showed you 2 years before the IceCube discovery. And then after IceCube discovered it, we looked at this peak and we looked at this data and said, well, actually, we wrote another PRL saying that, so here we predicted that peak, and here we wrote another PRL saying that that peak and the IceCube peak seem to be consistent. Okay? And this is, again, this is a component that is very easy to understand, right? The position at 1 PeV has to do with the threshold of pion production by protons on infrared light, right? So you need a proton of energy about 10 to the 17 to start producing pions, and from those pions you get neutrinos of factor 20 lower. That's where you get the PeV. So IceCube will have to wait for us to collect more data, but if indeed that component is a peak, which is very hard to tell at the moment, right? But if there is a peak component here, in addition to astrophysical power law on the left, that would be very suggestive of the secondary neutrinos. Also, the fact that you don't see nearby structures in neutrinos, but you see random distant sources, is suggestive with respect to production on the target, on the wall in between. Because nearby sources just don't have enough. There's not enough optical depths of photons between us and nearby sources to produce neutrinos in this fashion. And for distant sources, you get more of a thickness. Right? So then you expect the signal to be dominated by very distant sources collectively. And so you will see, for each neutrino, you can identify the blazar if it's nearby or a little further, right? You may be able to identify that blazar, but then the next neutrino will come from a different blazar. But collectively, it's the distant population that will dominate. So that's how we were going to find out. In addition, once we understand this beam, we can use it to probe the space between the source and us. Okay? And one thing we can probe is the magnetic fields. Now, magnetic fields in our own galaxy are well described by the models that Glenis and collaborators have produced. And it comes from study of cosmic rays and Faraday radiation and many different factors. So in our galaxy, we actually understand what's going on. But outside our galaxy, there's very little data. And people, if you look at the review articles. They quote the range from 10 to the minus 30 Gauss to 10 to the minus 9 Gauss. The upper limit is coming from non-observation of Faraday rotations, and the lower limit comes from semi-theoretical argument, which I don't have to explain because I have something better to offer. And for that specific blazar that I mentioned by telephone number, these people calculated what they think the magnetic fields should be like along the line of sight using constrained numerical simulations. And so what they get is, there's a range. These magnetic fields, depending on the model they use, could be going up to 10 to the minus 12 Gauss, or could be down to 10 to the minus 18 Gauss. So these are theoretical models. These are kind of blanket limits.
Is the human some coherence length?
The assumption is that coherence length is about 1 megaparsec. For we will use that for all the references that I give. In their case, 1 megaparsec is sort of the outcome of their simulation. Okay, but I will use that as a. But everything, all the numbers that I quote depend on the square root of that. Okay. All right. So can we say something about these magnetic fields using our newly understood mixed gamma ray and proton beam coming from the blazars? All right. So I told you that at the highest energies, the spectrum has a fixed shape, and we only have one parameter, the overall power. But at the lower energies, magnetic fields do modify the spectrum in the following way. The cascades do develop in a way that gamma ray produces E plus E minus, but then most of the energy is taken by one of those two particles and flies, and it hits a background photon, bumps it to high energy. Now there's a gamma ray again, right? So, but if you look for the leading particle in the cascade, that leading particle spends some time as a charged particle, as E plus or E minus. And during that time, the magnetic fields can deflect it. So if you're looking at a point source and magnetic fields deflect these particles occasionally, then at lower energies, magnetic fields will affect the spectrum. They will affect how many particles will appear to come from a point source. And so if you apply that, you get a lower limit on the magnetic field. And if you require that the protons are not deflected away from the line of sight, you get an upper limit. And so this is the range in which you can constrain magnetic fields. So these are magnetic fields in the voids, in deep space, right? Because again, the magnetic field near the source doesn't matter, because even if you make the protons run in circles, that's still a point source. It's just too far and too small. The magnetic fields here don't matter, because the gamma rays that we're observing were produced outside our local web of magnetic fields. So what matters is the magnetic fields along the line of sight, where they can slowly erode the point-like nature of the image. And that's what we're measuring here. Right? So this is a measurement, because there's an upper bound and a lower. Now, there is an alternative way to get a measurement, which is still controversial, and I'll tell you about it. But so alternative way is just to look at that point image and see if there is a halo around it from the particles deflected by magnetic fields. But from each individual blazar, you just don't get enough gamma rays to do this. So Shinichiro Ando and I tried to do this kind of observation by just stacking 180 blazars. If we superimpose 180 of them one on top of the other, maybe we can see a bell-like kind of shape of a halo around it. And we did see a 3 sigma effect when Fermi was only 1 year old, and when the point spread function available, the best available was the pre-flight calibration point spread function, and we used that, and we saw that the halos were there, just wider than the point spread function. But then next year, Fermi revised their point spread function and made it a little fatter. So, we didn't have a good claim then on this. Fine. But then recently, these people, Chen, Buckley, Ferrer, published a physical letter in which they used 8 years of Fermi data with 8 years of calibration for the point spread function. And they have a lot of lasers, and they claim they see the same halos. So if that result holds up, that magnetic field actually goes in the same ballpark, right? So the same range for the magnetic field. So this is still work in progress, right? So there needs to be more statistic, but it's something that seems to be reassuring that we are measuring the same thing in two different ways and seem to be getting similar results. Now, why is it interesting besides just putting it in Wikipedia, what these magnetic fields are? Well, it depends on where they come from. If they come from galaxies, then we can learn something about galactic winds and stellar processes and interstellar medium that we didn't know before if we know what the magnetic fields are. And if they come from the early universe in some form of magnetogenesis, then they can be related to baryogenesis. And this is kind of interesting because in the electroweak theory, the hypercharged current has something to do with the electrons versus anti-electrons, and it also has something to do with magnetic fields, and you can generate both of them. And there is this interesting proposal that by measuring helicity of magnetic fields, one can probe baryogenesis if, of course, these fields come from the early universe. And in fact, these people claim that they see 3 sigma evidence that helicity is there and that it has the right sign for the baryons image. Now, I am not in the position to defend their work. I haven't gone through it, but I'm just putting it out here as a potential direction where this can be. Yeah, it could be a new window on the early universe if we convince ourselves that these fields are primordial.
So is this independent of the model for baryogenesis? Or
this depends on the model, but if you use if electroweak anomaly is involved,
okay, yeah, then it makes sense.
right, and if magnetogenesis knows about that, right, then there's this connection, right? And so how are we going to know ever if these magnetic fields are primordial? Well, Warren had a very nice idea that with more data that CTA will provide, when instead of 8 blazars at these energies and distances, we'll have 100. We can actually probe the dependence not only on the magnetic field, but on the correlation links. And anything that comes from the early universe will have more power of magnetic fields on small scales than on large scales. Because in the early universe, the horizon is so small. So all models of magnetogenesis produce something on the small scales and then watch it cascade to the larger scales. So if we see that there's more power in magnetic fields on smaller scales, that is suggestive that it may be coming from the early universe. If it's something that's peak at 1 megaparsec, then it's probably astrophysical. So, but that's, again, this is a long game plan. Okay? All right, so now I'm going to stop talking about big black holes and start talking about small black holes. Okay, now for something completely different. And since we're already talking about the early universe, the Big Bang, it was a pretty big bang, and it was a place where temperature and density were extremely high. So obviously, it's one of the places where we should examine whether black holes were produced. Because whenever you have high density, you may expect production of black holes. And in fact, in the early universe, if you look at the plasma, the density is close to what it needs to be inside its own Schwarzschild radius. It's not that far. It's order 1 difference. Except, you never get fluctuations order 1 in the early universe. What you get is fluctuations 10 to minus 5 that we observe and which we can connect to the structures that were seeded by these small fluctuations. But there could be some processes that generate these very large fluctuations order 1 that you need to make black holes. So let me just remind you first that there are several distinct components in the universe. Most of the universe is dark energy. which doesn't seem to scale very much with expansion. Then there is dark matter, which is just like matter. And then there is, this little sliver, which is the stuff we understand. In fact, the more stuff we have, the bigger is the component, the less we understand. That's the analog of Heisenberg uncertainty principle. The more stuff we have, the less we understand. Quantity times understanding greater than 1. You can quote it as my uncertainty principle. All right, so how do we know these components exist? Well, fortunately, they make the universe expand differently. The stuff that is relativistic, radiation, has the density scaling with expansion as expansion factor to the 4th power. And that's because if you take a gas of photons, you expand it, the density goes down as expansion cubed, but then the wavelengths of each photon also goes down by the same factor. So that gives you the 4th power. If it is matter, then it just goes down as the scale factor cubed. And if it is a constant, then it doesn't change, right? Now, why does it affect the expansion of the universe? Well, think about this as thermodynamics problem. You take some gas under some piston, you expand it, the gas does some work, and it loses energy, right? Now, you fill that volume with a constant, you expand the volume, and it doesn't lose energy, it gains energy, because it's the same energy density times bigger volume, right? So in terms of work, it means negative pressure, and in terms of expansion, it gets energy out of nothing. Now, if you get energy out of nothing, you like expanding, you just keep expanding, right? So depending on how, of what stuff you put in the universe, the expansion rate changes. And the standard picture that most cosmologists accept is that in the very early universe, the pressure was negative, the universe was filled with a scalar field that gave it almost constant energy. And that created the stage for what comes next, and that is the radiation-dominated universe, which eventually was replaced by matter-dominated. Why was it replaced? Because the scaling of radiation versus the scaling of matter favors matter. So sooner or later, matter comes to dominate. Now let's suppose that there is a scalar field, either the scalar field like the Higgs field we discovered, or one of the scalar fields from supersymmetry, and the scalar field is just a number as a function of position. Okay? That's the simplest object in the universe. And then we can also talk about potential energy of that scalar field as a function of its intensity. So here's an interesting property that scalar fields have in the early universe. During inflation, during this very rapid expansion, scalar fields don't sit in the minimum of their effective potentials. They jump around. That's because in expanding universe, the energy is not conserved, just like it's not conserved in today's universe. Well, nobody is under the impression that energy is conserved. I mean, if somebody tried to mislead you into thinking that energy is conserved, they may have used some mathematical trick that proved energy conservation based on time translational invariance and something that was called Noether theorem. But of course, the expanding universe breaks the time translational invariance, so it doesn't apply here. I can take a very long chain and attach it to a star very far away, and the expansion of the universe will generate energy forever. So I can power my my desk light from that, right? So in de Sitter space, the energy is not the conserved quantity. There are plenty of conserved quantities, but it's not, energy is not one of them. And so the field can borrow energy and make a quantum jump somewhere. And it can make a quantum jump somewhere else. But it's very unlikely that it will jump right back to the minimum. It will probably keep jumping. Now, the way it would get to the minimum is by sliding down. But if the time scale for sliding down is very short compared to the expansion of the universe, then it's more likely for it to keep jumping. And so as long as the mass of the field, which determines the time scale, is small compared to the Hubble parameter during inflation, which is the horizon time, the expansion time, characteristic time scale for expansion, the field has a non-zero expectation value and kind of wobbles around the point where every degree of freedom carries energy equal h. That's the initial condition for what comes next. So eventually, when inflation is over, this field starts sliding down. And as it slides down, it doesn't remain homogeneous. Right? So it starts out homogeneous, but then it develops small perturbations, and it splits into lumps. And it's a generic instability that, there are mild conditions on the potential that it has to satisfy. But, for example, if the potential is in kind of logarithmic and has negative second derivative, then it's always satisfied. You always have an instability. And then these lumps decay. Okay, so you have a scalar field that started out homogeneous. As it was sliding down the potential, it became lumpy, and then the lumps decay. Who cares? Well, and this, by the way, is a very well understood instability. People study it numerically and so on. Well, if it happens at the end of inflation and before radiation really takes over, then something interesting may happen. You have a period of time when the universe is matter dominated. Right? So the scaling here is not like this, but like this. And that means it can come to dominate the energy density temporarily before decaying. And you can have a short period of time when the energy is dominated by matter. But that's not your ordinary matter. It's not the matter that has zillion of particles per horizon. It's a matter that has only a million particles per horizon. And a few particles means large Poisson fluctuations. Okay? So for example, this is a map of New York City during the day and during the night. And the spikes correspond to the population density. So people tend to work in bigger companies. So there are fewer bigger companies than there are houses and apartments. So you can see that the fluctuations are much bigger during the day because people tend to work in bigger groups than they tend to live in. And there are fewer fluctuations during the night. Right? So the fewer the number of entities, the larger are fluctuations. Or this is the addresses of billionaires in Manhattan. It's my dinner list for this week. And invitations. Anyway, so this again, you see that they tend to form regions where there are overdensities. And if you look at median income, then you will not see big fluctuations at all.
Why Trump Tower is not shown on the map?
Well, he's a billionaire with a negative sign, right? At least he was. Now he probably is changing the sign by bending all the rules. But okay, so here's the story. So the lumps, the scalar field comes in with very small energy compared to radiation. But once it is fragmented, it becomes matter with big islands of energy. These islands scale slower than radiation, and the scalar lumps can dominate the energy density. And then they decay, but during this time, you have matter with large fluctuations. Large fluctuations mean they can make black holes. So now,
what's the size of this lump?
right, so the size of this lump is from 1 to 10% of the horizon size at the time of fragmentation.
How is it determined?
Right, so this is, there are analytical estimates and there are these numerical simulations that people did, and invariably they see. So it cannot be bigger than the horizon size because of the causality.
Yeah.
And it can be much smaller than the horizon size because instability likes to be driven by very, very small wavelengths have too much kinetic energy, so that's not where instability will be the most. So it's between 0 and the horizon size. That means 1/10 of the horizon size. For lack of better factors.
But that variation in size probably depends on the potential, right? So
It depends on the potential in the sense that instability could be too slow and it will never develop to be anything to speak about. But for some range of parameters, it's develops and rips the condensate apart.
But the radiation also comes from the field. It's standard reheating. But
Right. So I'm not messing with the cosmological model at all. You can take your favorite inflation model with the standard reheating, and I'm just considering a spectator scalar field that wasn't doing anything interesting until it fragmented and became a form of matter.
Okay.
Suddenly it becomes the dominant form of energy in the universe. It says, oh no, I better decay quickly, and then decays. Okay.
So you weren't talking about the inflow of the
No, just a spectator scalar field that wasn't going to accomplish anything, and then suddenly it does this, right? And while it's doing it, we just count how many overdensities are big enough to make black holes. And even that is not enough. We count because, if that overdensity is not perfectly spherically symmetric, it's not going to make a black hole. It's going to make a Zeldovich pancake. So we only count those that are pretty spherically symmetrical, and they just kind of fall radially and make black holes. And it's a very, very strong suppression. It's very unlikely for that to happen. But the density of dark matter at this time is so tiny that even these very unlikely events are enough to make 100% of dark matter in primordial black holes. And specifically, this is where you can get this mass function or this mass function. So here, this mass function accounts for all dark matter in the form of primordial black holes.
Can you explain the shape a little bit of these?
Yes. So the shape. The period of time during which the black holes collapse is fairly short. That's why it's just one peak. If we stretch the parameters, then we can have a kind of flatter top and even two peaks, and then this collapse in between. We integrate over all scales there. But if it is just fairly short before the lumps decay, then you just get one size because there's not much expansion, right? And then just one size, that's the size. So I'm just saying that it's a delta function. Okay. All right, so this is a candidate event. So what my colleagues in Japan did, they used Hyper Supreme Cam, which is a fantastic instrument. It's unheard of. It's a detector. It's a photographic camera that weighs 4 tons and hangs in the focal plane of Subaru telescope. Right? So it hangs over the mirror. It actually, Subaru has such a strong frame that you can take 4 tons camera and put it there, and it will hang. And so because of that, they have a very wide angle that Subaru didn't have before the advent of that camera. And they can take pictures of Andromeda galaxy every 2 minutes, the whole galaxy. And they look for stars that become brighter and dimmer because a black hole passed the line of sight. So this is what the event would look like. In fact, in this paper, they report there's one event. They have to watch that star for a while now to make sure it doesn't do this again. Because who knows why the star did this. But this is what the detection would look like. But there's something else that I want to tell you in the last 10 minutes, and that is the effect of primordial black holes as they interact with neutron stars. So if dark matter or some fraction of dark matter is made of primordial black holes, these objects can fall in neutron stars with very small probability, but sometimes that happens. And if a black hole gets inside the neutron star, it just eats the neutron star from inside. And eventually, the end result is roughly 1 solar mass black hole. But in the process, if the neutron star was rapidly spinning to begin with, and now it's becoming smaller and smaller, then it spins faster and faster by angular momentum conservation. And the equatorial regions go in Keplerian orbits and material gets ejected. So something like 10% of that material gets ejected from this more and more rapidly spinning neutron star. And that material provides good conditions for our process nucleosynthesis. I'll explain in a moment what it is. And this may play an important role. And also I'm trying to raise awareness of neutron star systematic destruction by primordial black holes. So, as I said, the neutron star inside the black hole makes, it eats the neutron star, the radius decreases. You can actually convince yourself that angular momentum transfer is efficient and that accretion is spherical, mostly spherical in these later stages of accretion. And so there is a substantial release of material. After our paper came out, David Radici from Princeton said that he wanted to see whether numerically he can simulate this. And so this is the movie, these preliminary results. He is simulating a black hole that you can see it's coming in, and that black dot is the black hole, and it's eating away the neutron star. And all this orange and red material is the neutron-rich matter that is that is ejected, and the amount is consistent with what we had in the paper. So this is the this is the black hole. This little dot is the black hole, and then it becomes bigger dot, and then at the end it carries whole solar mass of energy. So it's like 3 kilometers across.
So for other objects, it just goes through, or why not white dwarfs or
Right. The other objects it just goes through. Absolutely, absolutely. It doesn't get stuck in a ordinary star or in a white dwarf. In fact, even with a neutron star, it first goes through, but it loses enough energy to come back, and then eventually it gets captured. Yeah. Okay. So our process nucleosynthesis is the origin of gold and uranium and platinum, and the abundances of these elements are very well understood in terms of the actual processes that you need, but we still don't know where these processes take place. So if you look at the abundances of heavy elements, you see these majestic peaks at gold, platinum, uranium atomic numbers. To build these peaks, what you need, so this is neutron number, this is proton number. If you're trying to add a neutron to a nucleus here, it just doesn't want to stick. It will eventually cause the nucleus to fall apart. But if you start out here where there are many neutrons and fewer protons, and let the system evolve from here down in this direction, then it gets attracted to these islands where the nuclei are stable, and you explain extremely well the abundances of these materials. So what you need is high neutron density material with low enough temperature. High temperature doesn't work. Okay? So neutron star collisions are good. And in fact, this very famous event that was recently observed, the neutron star mergers, it is a good confirmation that this stuff is happening. But if you look at the models that people produced before the merger, they simply wouldn't work because the temperature inferred from the optical afterglow would be too high to produce these heavy elements. Now, if you make the model more complicated and assume that there is a 3-zone emission and that the bluer light comes from a different place from where our process takes place, then everything can be made consistent. But that's, again, there's no proof that this is the site of our process nucleosynthesis. So if there is some destruction of neutron stars by primordial black holes, that can be a significant contribution to our process nucleosynthesis. It would also explain the peculiar distribution of heavy elements among dwarf spheroidal galaxies. The distribution, of gold among dwarf spheroidals is just like distribution of gold among humans. One has a lot, and the rest of them have none. So reticulum 2 is very rich in these heavy elements, and the rest of the dwarf spheroidals show no R process. So if you estimate the probability of primordial black hole being captured by the neutron star, it's a small probability event, and so that would be consistent with this picture. You would have to have more than a few percent of of dark matter in primordial black holes to explain all our process, or you can have part of our process explained by smaller abundances of primordial black holes. It is also something that allows you to look for primordial black holes, because the reason this constraint doesn't extend below 10 to the minus 10 solar masses is because the Schwarzschild radius becomes smaller than the wavelengths of light, and you don't get any microlensing. So how are you going to look for primordial black holes in this mass window? Well, if they do exist, they would invade the neutron stars occasionally, and the end result would be a one solar mass black hole. And so you would see some population of one solar mass black holes, which cannot be produced otherwise, because astrophysical mass function starts with more than 5 solar masses. And it's very difficult to produce one solar mass black hole. Whereas here, if you do see some population in gravity waves or something else, then it would be indicative of, it would be consistent with some very small black holes invading and converting neutron stars. Another way to see this process would be to observe a kilonova type signal in optical light, which is the sign of our process nucleosynthesis, without a strong gravitational wave signal. Because the end stage of this process is a fairly spherically symmetrical configuration, unlike two neutron stars merging, which is a very much non-spherically symmetrical. So the production of gravitational waves here is suppressed. So if you see a kilonova without an accompanying gravitational wave signal, that's more likely to be something like this. And interestingly enough, you can produce 10 to the 50 positrons from these events, from shedding nuclear material in these quantities. And that would explain the 511 keV line observed from the galactic center. And finally, if you take a magnet, neutron star is a big magnet, if you take it and massage it on the scale of milliseconds, you're going to see a millisecond long radio waves burst. And there are fast radio bursts which one can try to connect to these events and explore whether one can detect them in radio waves. So all of this makes a good story, and this story was, this is a postdoc, Vladimir Tahistov, who is a postdoc at UCLA, and Eric Kotner is a graduate student who did this work, and then DOE Office of Energy, Office of Science in the Department of Energy listed us as one of the top 5 stories so I thought, if they thought it was a good story, maybe it's a good story to tell you. So that's why I want to talk about it. So thank you, and I can take questions.
Questions, please.
Many years ago, when in high school, I read all the elements heavier than iron are created in supernovas. So you said that that's
very good. Okay, very good. So up to iron, there's no problem with creating elements in a supernova. Now, beyond iron, we need cold nuclear material. Well, no problem. Supernovae make neutron stars, and some of that neutron-rich material may get out. The problem is that now we understand the emission of neutrinos from cooling neutron stars, and anything that is neutron-rich to begin with gets exposed to equal number of neutrinos and antineutrinos. And if you do that, it equalizes the proton and neutron numbers. And so you may start with a neutron-rich material, but after being irradiated by equal number of nu and nu bar, neutrinos and antineutrinos, it becomes kind of equal proton-neutron material. And forget nucleosynthesis at that point, right? So people tried to rectify it by postulating a sterile neutrino into which one type of neutrinos could convert, and then you still preserve the neutrons. But that is significant step beyond the standard model. So supernova by itself cannot produce our process nucleosynthesis. Neutron star mergers are a very good candidate, but there's still open questions, and we still don't know for sure whether that's where the bulk of our process takes place.
More questions? Just a quick one. What happens with the Zeldovich pancakes that you?
Right. So if we have some dust like these particles here, which are not are not spherically symmetrically distributed, right? Then the shape of this cloud evolves so that the shortest axis becomes shorter faster than the longest axis.
Mhm.
So the collapse leads to formation of a pancake.
Right.
And then, you can form some configuration which exists on Keplerian orbits, but never ends up in a black hole.
Right. So that's some kind of prediction. I mean, that's what I'm asking. Whether
But then, right, so that would be a prediction, but then these lumps just dissolve and become part of radiation, right? So anything that doesn't become a black hole during that temporary
Right.
domination by lumps,
Right.
everything else gets dissolved in radiation.
Right. So question will be how long? I mean, if it might affect CME and isotropy
Yes,
or not? or-
yes, that's right, that's right. So in the models that we discussed, everything happens at very high temperatures, at temperatures well above 10 to the 6 GeV.
Mhm.
And then there's no remnant from anything except black holes.
Okay.
However, if you want to go for this part of the mass function, if you want to produce black holes with 10 solar masses that LIGO would see, you can even get 100% if you don't believe these constraints. I just don't want to. But in this, for this mass function, you need a very light scalar field that fragments very late,
Mhm.
and then your question becomes very relevant, right? Because this happens around just before nucleosynthesis. But if you go to even larger masses,
Right.
it may affect nucleosynthesis, it may affect CMB. Right?
Any more questions? Oh, Kevin.
Can you make supermassive black holes?
Yes, that's right. And so we have a paper by Kawasaki, Yanagida, and myself where we create black holes of 10 to the 5 solar masses. And those are the seeds of supermassive black holes that form later. And people have shown that if you can make 10 to the 5 solar mass, you can bridge the gap and march towards billion solar masses.
I mean, the usual growth.
Right, exactly, that's right. It's going from 10 solar mass to 10 to the 5 that is problematic. The other part is fairly easy.
Okay, if no more questions, then thanks to Alex again, and everyone is invited for wine and cheese.